There is a revolution going on right now, a revolution in lighting. And you're probably wondering what that has to do with evil rubber ducks, right? Well, every revolution has to have secret agents and rubber ducks. LED is not only changing the way we light things because it's so much more efficient than incandescent or halogen sources, but also generates so much less heat, and it's so much smaller. Here we can see a diode right next to a penny. Not to scale, of course. So the diode and the penny are to scale, but I don't know. There's some other advantages with LED, and we'll talk about some different types here and what those advantages are. A few of the very common types of LED, 5mm and 10mm, as we see down here, so cleverly named because their diameter is 5 or 10mm. We lighting people, you know, are a clever bunch. Or SMD, and those we see various wattage assignments. Another clever name for you here, SMD, is surface mount device. Or COB, which is chip on board, and that's what you see in the lower right. When we talk about 5mm and 10mm diodes, we typically see color combinations like red, green, and blue here, each diode being an individual color. When we get into SMD, we'll often see things like 3-in-1, 4-in-1, 5-in-1, hex, 6-in-1 diodes. And the reason, and we're going to focus primarily on RGB, the reason for this is by using red, green, and blue, we can make just about every color that the human eye will see. And in fact, the screen that you're looking at right here is comprised only of red, green, and blue pixels. Clever little Venn diagram. The reason this works is because our eye principally only sees 3 colors. Unless you're tetrachromatic, then you see 4, and that's an entirely different TAD talk. But for tonight, we're just going to talk about us trichromatic folks. And our brain interprets the varying intensities of red, green, and blue light that it sees, and it tells us what color we're seeing at that point. Which also brings us to pink is a figment of your imagination. That's yet another TAD talk for another time. Looking for the shepherd hook right now. All right, pop quiz. Here's our evil rubber duck. If we take a look at the piece of paper down here, on which we have a rubber duck, a banana, and a rubber chicken, don't ask. That was the punchline. Pop quiz. What color does the paper look to you? Yellow. All right. How about the rubber ducks, the banana, and the rubber chicken? Orangish? Reddish? All right. I'll bet you're on the edge of your seats wondering why, aren't you? Either way, I'm going to tell you, okay? We're lighting these objects with yellow light, but it's not yellow light. We're lighting this object with LED yellow light. And one of the reasons that LED is so efficient is it has a very focused spectral output. And so we don't have yellow light, we have red and green light. When that reflects back off the paper, the white paper reflects the full bandwidth of light. Our brain sees some red and green and says, well, that's yellow. The problem is, with our duck and banana and chicken, we have pigments in there. And the pigments only reflect back certain wavelengths, and they absorb the others. And that's why we see those as color when they're lit with full spectrum light. Well, if we had yellow light, we would see a yellow duck, but we don't have yellow light. We have red and green light. So only some of the wavelengths are reflected back, and thus the duck appears to be orange, because we're seeing more of the red wavelengths reflected back to us. Plus, the duck is evil. Thank you for laughing at that. I worked hard. You know how hard it is to draw that in PowerPoint? Slaved all day over a hot stove for that. See, when we're talking about RGB color mixing, and there we're talking about additive color mixing. The more color of light we put in, the closer to white light we get. White light is comprised of a full spectrum of colors. On the other hand, we talk about pigments and dyes, things that would maybe make this shirt look this lovely Bemidji State University green. As we add pigments, we get closer to the absence of light. More wavelengths are absorbed, less are reflected back, and we get black. When we make white light with LED, now there are white LEDs, in fact I'm being lit by 2 bright white LEDs right now, but when we make white light with red, green, and blue LED, we can see this narrow spectral output. Versus on the right, there's the spectral output of a halogen lamp. So rather than using combinations of these red, green, and blue diodes to make a color with LED, with a halogen light, we would use a theatrical color filter, a gel. And here we can see the gel for yellow light. We're kind of sticking with the yellow theme here, got it? And what we can see is it filters out most of your wavelengths beneath green. And so we leave the green and red light and the yellow, in the middle, and we see yellow. You're waiting for another duck, aren't you? It's not coming, sorry. Now we're on to the secret aging part. Everybody get to play with these as a kid? Or recently? What we have is we have a white piece of paper on which is printed red and blue ink, and then we have just a red gel that goes in your secret decoder glasses and reveals a secret message like drink more Ovaltine or something. And Norm, only your generation got that joke too. Yeah. And so what we have here is that when the white background of the paper reflects the light, the red gel filters out all but the red wavelengths. The red ink reflects back red wavelengths, and so we see that as one color, but the blue ink absorbs the red wavelengths and doesn't reflect them back, so we don't have much light being reflected back there, and then you can see your secret message. And this slide I left in just because it said SPY on it. I thought it was pretty cool. What's this have to do with you and exhibits and lighting? Well, we can take advantage of LED, and we can take advantage of the ability we can mix colors quickly and easily using combinations of red, green, and blue light from very small, very power efficient sources. We can put them just about anywhere. We don't have to worry about the trees catching on fire, for example. At least, I hope not. Till I'm gone. I'm out of here in 5 minutes. Recently, I was given the challenge of lighting a charity event for an air museum. And of course, one of the big ticket items there was a car. And they wanted to get top dollar for it. The whole point is to raise money, right? So the car has to look good. They wanted it to really pop out, and they were trying to light it with white light, and they said, it's just not working for us, and this is a pretty big ticket deal. So I said, well, let me take a stab at it. And by using the ability to change the intensities of the red, green, and blue, I said, I'm going to not only find the color combinations that light the car well, but I'm going to try to find ones that really work with those pigments and pop, make that thing really come alive. And this is what I came up with, and they were super happy. They said, holy cow, that thing just jumps out. And there you go. Physics can be your friend, just put it to work for you. That's all I have. Thank you.